Hey there, everyone. Welcome to another session of Global Hack Week. Today we are on day 4 currently, so we still have 2 more days to go, and we're almost wrapping up with day 4. This is one of the well, at least in my time zone, it's a night stream, but if you were located at the other end of the world, it's probably a morning stream. So I'm really happy to be back. I know that for this Global Hack Week, I've been doing a lot of robotics streams, especially focused for beginners. So we had the Arduino stream. Then I had the what was the second one? Uh, I'm not sure why I'm forgetting. So we had the Arduino, and then the other one. I know this one. This one is gonna be about embedded systems, but then I hosted another one recently. I'm not sure why my memory is. Oh, it was about PID controllers. Okay, I think I'm just too exhausted from just like everything, and my memory is sometimes just failing. But hopefully for today, I already have all of the content prepared for you. It just a heads up. This is gonna be a short stream, so we're just gonna spend about an hour talking about embedded systems, and I'm also gonna show you a cool exercise at the end. So on other previous streams, so such as the Arduino one and the PID controller one, there were some hackers that were asking about how does the Arduino functions actually work on the backside. So today we're going to be seeing an article that explains how does it all relates, and I'm also going to be showing you like all of the explanation that's on the other side of embedded systems, such as controllers that we know today. I just want to start by introducing myself for people that don't know me. So my name is Jocelyn. I'm a coach here at Major League Hacking. I'm based in Mexico and I study robotics, so that's why I always like to make streams about this. I do some research in neuroengineering. That's what I'm doing right now for the winter. I also work as a cloud engineering engineer at a tech company. I like bee plushies. I collect them. What else? Yeah, I'm also part of the fellowship program. I was a fellow myself. That's how I entered MLH, and then now I just help basically as a project manager to all of the different projects that they have, all the different batches that we do on the summers, winters, and springs as well. So if you have any questions about anything related or unrelated to the stream, feel free to drop them on the chat. And don't forget to check into this stream because that's your way of getting your points for the weekend so you can earn our basic swap. Great, so let's just get started. For today, we have a packed agenda of things that we need to get through the hour. So I just wanted to understand first what is the meaning of beats and binary in embedded systems. Then we're gonna see a relationship between Arduino and bare metal. We're going to see data types and sizes for the different data types. Bitwise operations, I'm not going to go a lot in depth into bitwise operations just because I don't feel that we have that much time, but I will definitely point you to the correct resources so you can research more about them. I'm going to explain registers and memory mapping. And finally, we're going to see how to do a basic code. First in Arduino and then in bare metal. I'm going to share a really cool article that I found, and I want us to see that example as well. So my goal here on this stream is that after this session, you will understand at road level bare metal in embedded systems. So everything that we're going to be seeing today, it's what we do in actual robotics. So Arduino is just a phase, and then once you finish like everything that you can optimize with Arduino, you move on to bare metal, where all of the actual controllers of the industry are based, such as the STM32 family. So today I'm going to show you how everything works on the backside, both the code and also the hardware setup, so you can understand. And now the next time that someone talks to you about microcontrollers, you can be more of a nerd and explain them at a more technical level. So first of all, we want to understand the importance of binary in bare metal, because I'm pretty sure we've all heard that zeros and ones are the basic of everything in computers. But to be honest, have you really wondered, like, how does that really translate to computer code and how does it actually work? Because at least when people told me about that, like, oh, everything's in binary, I was like, yeah, but like they're just zeros and ones, and I know that zeros and ones can represent numbers like in hexadecimal or in decimal system, as we know, but how do they actually convert into instructions or code that a computer can actually execute and do things? So that's my goal here today. We're going to understand how those zeros and ones actually mean something to your computer, and we're going to relate it to embedded systems. So zeros and ones are just basically having direct hardware communication, which means register level access. If you're not familiar with registers, I'm also going to explain that in the upcoming slides. So having control of your bare metal hardware, it means that you can control individual bits for every sensor, for every actuator, or basically anything that you have on your system. So by having control of individual means, yes, I'm actually meaning like changing a 0 to 1 and a 1 to a 0. This is also very important because we are being memory efficient. So in really large operations and industrial systems, it is very important that we are efficient with memory. So maybe at your school project, like it doesn't really matter if you have like, if you spend like 32 kilobytes in whatever like file. But now when we're talking about industrial and professional systems, those 32 kilobytes are actually important, and we need to find the best way to optimize it. Or sometimes we have a restricted amount of memory that we can't use. So that's why it is important that we know how to treat these operations so we can optimize at its max potential. And yes, it is very important. A little recap of binary. Binary is just basically zeros and ones. One is on and 0 is off. And when you do combinations of these zeros and ones, you can actually represent like different numbers. And all the code that you know and all the data that you know is reduced at the end to bits. So only zeros and ones. And if you are familiar with number conversions, you will know that binary system is base 2, and then we have our decimal system that's base 10, and then we have hexadecimal system as well that we're going to be seeing why hexadecimal system is also important. So there's different types of numbers. If you already took like an introduction to CS at your either high school or your beginner courses at university, I'm pretty sure they taught you like how to convert from binary to hexadecimal. But I mean, to be honest, when I was going through that, I said to myself, like, okay, why do I really care how to convert like a binary number to an hexadecimal number? I mean, it's cool to know how to do it, but like, how does it actually going to help me? Honestly, it's not going to help you a lot, because at the end, you're not the one that's going to be converting those numbers on your computer. The computer is going to do that itself. But it's nice to understand how you can play around with numbers, so you can have different representations in different bases. All right, so moving along, we basically just saw why binary it's very important for embedded systems. And now moving on, now making a bit of emphasis on Arduino, which is something that most hardware people are familiar with, because Arduino, it's a basic, beginner friendly that most people that want to get into hardware start with, and it's a really good start, to be honest. And then making the comparison with bare metal, which is basically the foundation to everything, it's very different. So for Arduino, everything is really abstract. So it is basically a simplified API. It hides all of the hardware details. It's really quick for prototyping. So if you just want to get a quick start project and just get started, Arduino is your go-to. All of the libraries are pre-written. So you just basically, if you just want to turn on a LED, you basically just call a function and it's going to work. The only downside is that you have less control over timing and the resources that you have. So in Arduino, like using your regular Arduino IDE, you are not able to manage memory, and you are also not able to control timing or the internet clock of your Arduino as you would like when you are using bare metal. And then for bare metal, which is just basically having direct hardware access, you can manipulate directly each of the registers. I'm gonna explain that in just a second. You have precise control of everything. You are being very efficient because you can basically control everything in your system. And I mean everything, like literally everything. But there's a couple downsides. You need to have deep hardware understanding and knowledge, and you also need to read the data sheets. So every time that you purchase a microcontroller, you kind of have like a getting started manual, and that manual is called a data sheet, where you can see like all of the memory mapping, the input and output ports, the registers, and how the addresses are being organized. Bare metal is just basically the foundation for all embedded software, including Arduino libraries. So even Arduino is written in bare metal, but you are basically not seeing that because someone else already did it for you and basically just handed in all of the work, so you can see, the nice functions being called, and you just don't have to worry about everything. And now this phrase in here that says bare metal is the underlying reality, and abstraction layers like Arduino are built on top of bare metal. So Arduino is just basically a shortcut into writing direct bare metal code. So my goal here today is that we understand how bare metal works on the downside. So now when you see an Arduino, you can understand what's going on behind of it. So I mentioned a bit about data sheets, and data sheets are like your manual when getting started with your hardware, and they're very important because they're the source of truth for the hardware. I mean, yes, of course, you can ask ChatGPT or you can ask Gemini, but sometimes even these tools, as they are trained up to a specific date, they might not have access to like these manuals. So my recommendation there, if you want to use these AI tools, download the data sheet and upload it to your favorite AI, and then you will get like really nice resources. We have a question in here: is bare metal a software or hardware? Bare metal is basically like your board. It's just a way of calling it. So for example, when you want to code something, like specifically in the hardware, you say like, oh, I'm gonna do this C code in bare metal. And by saying bare metal, it means that you are going to code directly into the hardware, like very, very specifically. So I wouldn't say it's not a software, and it's more pointing toward the hardware side, because bare metal is basically like the board that you use. And then the code that you're going to be writing, it's going to be a code that can adapt to bare metal. So basically your board, like for example, your Arduino or your Raspberry Pi or your STM32 or whatever a microcontroller you're going to be, whatever embedded system you're going to be using. Hopefully that was clear enough for you. Let me know if you have any more questions. Okay, so going back to the data sheets, as I was saying, you can download these data sheets online, and then you can just upload those into your favorite AI so you can get like better code. I also recommend reading like specific sections of those data sheets, because in there you can find key information such as the pins that you can find in your board. As we were seeing on the past stream in Arduino, we understood that there's different pins, like for example, the analog pins and then the digital pins. On the data sheet, you can basically find like all of the pin map and everything, so you can connect all of your components properly. You also have your electrical characteristics, such as how many voltage you can receive and how many current you can resist. Then you will also find the register maps and the memory layout. We're going to see that in just a second. And you can also find your timing diagrams and protocols, such as how to connect your board. So you can have, for example, SPI, WART, or whatever protocol you are going to be using. I'm not going to be explaining that a lot into depth, because that's a whole other different topic about communication protocols. But if you are interested in, you can just type in Google like communication protocols. because they're very popular among hardware, because when you want to communicate between two systems, you need to use communication protocols. So that's just another topic. All right, so we basically just covered a bit of an introduction into how do you compare Arduino versus coding in bare metal, and then also like introduction to a binary. And sorry, and now it's important to see the different data types. Why? Because in hardware we do care about space, and we do care about how much memory you have overall. So it's important to understand the different data types that are out there. So as I was saying in the beginning, we have different number systems. So in here we have the machine code, which is basically the binary. Then we have the hexadecimal code, and then we have the assembly code. If you want to learn a bit more about this, and specifically how to code in assembly, I have another stream on the past beginners week that's called coding in assembly. My bad. Coding in Assembly 101. If you want to take a look at it, it's also on the live streams from MLH on our YouTube channel. All right, so moving on, understanding the basics on binary and hexadecimal systems. So I'm not going to be explaining you how to convert binary to hexadecimal. Here's an example, but yeah, you can just look that for yourselves. I mean, to be honest, it's not really like a big deal. I just wanted to understand that you can convert in between these two. So binary, as I was mentioning, it's base 2, and it's an actual language of computers. You can only have 2 digits, like 0 and 1, like 1, 0, 1, 1, 1, and so on. So basically how computers talk. And then we have hexadecimal, which is base 16, and it's a shorthand for binary, and it supports digits from 0 to 9 and letters from A through F. One hexadecimal digit is equal to 4 bits. That's really important. So if we want to see like our relationship between those two, hexadecimal is just basically a shortcut for binary. So that's also like something to keep in mind. And yeah, thank you for doing that. That was basically to convert the 10101100. Awesome. So I'm not sure. A 2-bit. Okay. So as I was saying, one hexadecimal digit, like this hacker placed on the chat, is equal to 4 bits. And if we see in here, we have we have like 2 bytes. No, sorry, no, 2 bytes. No, 1 byte is equal to 8 bits. We have one hexadecimal digit is equal to 4 bits. So basically, to convert, you just take you can take chunks of 4. So you divide from the least significant bit to the most significant bit in order to convert. No worries, you're all good. Awesome. So from this slide, I just wanted to understand that we use hexadecimal as a shortcut instead of just using binary. Because imagine you as a person like typing the whole binary direction in your code. That's going to be really long. So instead of doing that, we use hexadecimal in our code, so it's faster for us to type and also to understand. And now moving on to the different data types and sizes. I'm pretty sure that maybe when you were solving lead code problems or when you were coding something, you've seen these types of structures like unsigned integer 8, unsigned integer 16, and unsigned integer 32. So maybe you've been using them randomly. To be honest, I've also done that as well. But in hardware, it's really important to use these types of data types. Because if you only have like, I don't know, 32, instead of using like a really large integer, you can reduce the amount of bits that you are going to be using on your data type. So for example, the smallest one is this one, unsigned integer 8. It has 8 bits, so it's only 1 byte. And then 32 bits is 4 bytes. So let's say that you want to store like this number in binary. Oh, I typed, my bad. I was meant to be doing this. So let's say that you want to store this number, this binary number in a variable. So if I were to use the unsigned integer 32, I'm just basically going to be wasting a lot of bits. So instead of doing that, I can use my unsigned integer of 8 bits, and I will only be like misusing 4 bits. because this one takes up 4 beats. So 1 is 1 beat, 0 is another beat, 1 is another beat, and the other one is another beat. So we have 4 beats in total. So I'm basically saving space. So maybe you're wondering, like, okay, 10 beats is basically just nothing. But when you're working with hardware, it's very important to optimize as much space as you can, because you can use it for something else. So we always want to be as much more optimal as possible. And this can also relate a little bit into the CS side of computer science side of like solving problems. Because sometimes when you get those typical data structure problems, maybe you can talk also about your memory management on your code, because they ask you about time and space complexity. So on the space complexity section, you can also discuss some of these trade-offs when you are talking to your interviewer, or and so on. And yeah, it is important to use these different data types in robotics, because we ensure that the code behaves consistently across different processor architectures. And we are also using the exact width, which is also important for interfacing with hardware and registers, especially for communication protocols where bit counts matter. So I know that I mentioned that I was not going to get a bit into depth in communication protocols in robotics, but it is also very important that you can dedicate the specific amounts of beats that you want to use on communication protocols, because the beat count actually matters. Why? Because each beat position means something. So for example, if your beat is in position number 5, then that position number 5 is going to mean something. So if you are like misplacing beats, then your hardware, it's going to be super messed up. I really encourage you to look up for communication protocols in hardware, so you can learn a bit more about them. Maybe on another Global Hack Week, I can make a stream about communication protocols, because it's also really interesting. All right, so moving on, I'm going to go into bit manipulation. I'm not going to explain almost everything on these slides, because to be honest, there's a lot in there, but I want to make my best so you can get at least an idea of what I want to explain in here. Because we're going to be seeing that a bit further on the example at the end. So bit manipulation, there's something called bitwise operations. And I really encourage you, if you want, to check a YouTube video on bitwise operations, because it's a whole topic. So these are the things that they ask me in exams. That's why I just like seeing all of this again. It's bringing me back memories from school. I mean, I'm still in school, but it's just remembering like those classes of explaining bitwise operations. Basically, a bitwise operations is manipulating specific beats without touching other beats. And maybe you're saying like, oh, why do I care if I touch like different beats? Because I was saying every position matters in hardware. So if you misplace beats, you are going to be sending the wrong message to your computer. Right. So for bitwise operations, we have different logic gates. So there's AND, OR, SOR, and NOT. So if you've taken a crash course on computer science, maybe you've seen a bit about logic gates and the diagrams, like how do they act actually like in beats. And maybe you were saying like, oh, these are cool diagrams. Like it's cool that I can convert a 0 to a 1. And now the actual process and the actual function of these logic gates is related to bitwise operations, because you can basically transform your bits into different things, so you can manipulate them into being something else. So we have an example in here. Let's say we have our register A. So we have a value in here, 1 0 1 1 0 1 0 1. And let's say that I only want to modify like specific bits from that register. So I apply a mask that has an and then I have my result in here of A mask of B. And then I have my result. Then we also have bit shift operations, which is just basically shifting bits either to the left or to the right. And there's nothing too complex about these. I mean, it's just moving them like either to the left or either like to the right for the amount of bits that you want. Like for example, in here, we're doing a left shift, which basically means that I'm moving the 2 1s that I have in here to the left onto a spaces, So basically from this slide, what you need to know is that you can apply logic gates and bit shift operations into molding bits in the positions the way that you want them to be in. And this is very important because they actually mean stuff at the moment when we are doing our code. So here are some common techniques to change specific bits. So for example, if you want to turn on a specific thing, you are going to be doing this. So you're going to be shifting one and doing I think that's an OR. Yeah, that's an OR. And then for clearing a specific bit, you do an and then you do a not, and then you do these combinations. So if you're seeing in here, this is just for clearing a specific bit, and then this one is for setting a specific bit on your register. There's a combination of the different operations that we have in here, such as the and, or, so, or not, and then the left shift and right shift in here. Here's another example of visualizing this shifting, showing how shifting 1 to the 5 creates a mask that targets only the 5th wire. So this is the initial value. We have a lot of zeros, and then we have a 1 in here. And then if I apply this operation, the 1 and then like the 2 alligators like these, that basically makes everything shift in here. So the 1 bit is moved 5 positions to the left, and the new position, basically the bit 5, is set to 1, while all of the other positions are still 0. And this basically creates a mask that targets only the 5th bit. To be honest, it's not very if you wanna test these yourself, because at the end, these operations, like these ones that are in here, are the ones that you're gonna be writing in your actual code. To be honest, I struggle time to time with these operations. I have to remember them once in a while. But you can always ask, there's bitwise operation calculators online that you can use. Those are really handy. You can also ask ChatGPT or whatever. We have a question in here. What's the essence of shifting? So basically, on your hardware, you have these spaces in memory, right? And each space in memory, which is a specific bit, has a meaning. So every position has a meaning. So if you want to play around with the meaning of things in your hardware, you need to do bit shifting. Well, basically bit manipulation. So apply logic gates and apply bit shift operations. Here's a list of all of the bitwise operations that you can use. We have the and, or the ones complement, which is basically the not, left shift and right shift, and then we have some examples in here of how they actually operate. So basically from here, you're gonna understand these a bit better when you see the code. For now, you just need to understand that sometimes we need to play around with our bit arrays in order to do the behavior that we want in our code. So basically in our hardware. Okay, so now we're gonna move on to registers and memory. I promise this is more simple than the bitwise operations. To be honest, bitwise operations can sometimes be a bit tricky, and they're also a pain and a headache because they're just so messy. And then for registers and memory, it's just understanding some of the concepts. So basically, registers and memory, we have input and output ports in robotics, right? So this is an STM32 pin out, and the input and output ports are really important because it's how you access hardware by writing to a specific memory map registers. So for example, we can have a GPIO register that controls an LED. So from this diagram, if you see, I basically circled with red a specific input and output port, which is a GPIO register. And that specific pin can control an LED, it can control a motor, it can control a switch, or whatever you want to control in there. So as we were seeing on the other stream that was related to the Arduino, if you recall, there's different pin configurations for your Arduino. It's the same for the STM32. You have different pins that you can configure for different stuff. So from here, it's just important for you to know that there's input and output pins on whatever hardware that you use, and they can be used for whatever you want to plug in or read values from. All right, so I've been mentioning quite often registers, so now it's time to understand that. So registers is basically a space in your hardware. So it's like I'm not sure how to explain these, but register is where you actually store the bits. So we have general purpose registers that are like register 0, register 1, register 2, and so on. So we go from 0 to 15 registers. And we know that 32 bits is equal to 4 bytes. So they can store 4 bytes in each of these registers down here. And each register, it can store different things. It can store a memory address, so a memory that you want to keep. It can store an integer that has a sign or doesn't have a sign. You can also store different bit patterns like flags or masks, which is basically what we saw earlier. So in here, we have general purpose registers, which are the ones that don't have anything. But then if we see in here, register 13 is used as a stack pointer, register 14 is the link register, and register 15 is the program counter. And then we have another special register in here that I'm not going to explain. Again, if you want to understand these a bit more specifically, I have another stream that's called Coding in Assembly, where I basically explain all about registers and memory mappings. For today, it's just important that you understand that registers can store bits inside of them, and approximately they store about 32 bits per register. So every hardware that you see, it has registers. So your computer, your STM32, whatever you use that's like a physical hardware that can store something, that can store values, has registers. It just depends on how many registers you have per each hardware. We have a question here. Hi, is it possible to share the slides? Yes, for sure. I can share them throughout Discord as well. And there's also the recording online, so you can always watch the YouTube video and go through the slides and take your time as well. And you can also ask me questions through the stream, or you can also reach out to me directly via Discord. All right, so I'm not going to be diving into these very specifically, but there's some registers that are called special registers, such as the program counter and the stack pointer. For the program counter, it just basically holds the addresses of the current instruction that's being executed. So if you have an instruction that's adding 1 + 1, your program counter is going to store that instruction. And then for the stack pointer, it works as a stack. It points to the top of the stack in memory. And stack pointer is also used to store temporary values. So if you want to store something that you don't want to keep, you can store it on your stack pointer, which is a specific, it's a special register. So if we go back in here, we can see that the program counter is on register 15, and then the stack pointer is on register number 13. All right, so let's move on. There's also other two different types of special registers. We have the link register. This basically stores the return address when calling a subroutine. We have the CPSR. This one is the one that holds condition flags. So basically when if I want to explain these, I need to explain a lot of things. So maybe let's just say that CPSR is a really specific register. If you see down here, it's all the way to the end. So when we are coding in assembly, and if you are familiar in coding with assembly, you will know that you cannot just code directly like you were doing in Python. So for example, to do a loop, you cannot just say if 5 is greater than 1, do this, else do this. In assembly, you cannot do that. So the way that you do this is by comparing different registers and setting specific flags. So the current program status register, which is the CPSR, it actually allows you to hold those conditions flags for your code. Like for example, -0, carry, or overflow as well. And These flags are set depending on the comparison result and branch instructions, which come from the code that you are writing. So everything that's going to be stored in these registers, that's up to you. So that's something that you do on your code. So if you say, okay, I want to store a number 5 in register number 3, that's something that the programmer has to do, like that you have to do in order to store and play around with these things in here. Okay. Then another important thing to understand is words. So in computer architecture, the term word basically means the natural size for the CPU. A word is equal to 32 bits, and word size changes between architectures. So depending on the architecture that you are based in is the size of the word that you're going to be having. So in here, there's nothing like, there's not much to understand. It's just a concept like that a word is equal to 32 bits. So 2 bytes is equal to 1 word if we see in here. So we have byte 0 from 0 to 7, and we have from byte 8 to byte 15, and that's basically like word 0, and then so on. And a double word is just basically having 2 words together. Okay. And then going back to the relationship between binary code and how does it actually execute. So instructions, an instruction, and that's something that you are sending into your code. It's just nothing more than a 32-bit binary code that tells the CPU what to do. Like, for example, move data, do some specific math, turn on a specific LED, do a comparison, or so on. So in assembly, you will write something like this, and then that code gets translated to machine code, which is binary. So that's why I was saying that everything, every code that you do in C bare metal, it's going to be translated to assembly, and then that's going to be moving on to machine code, which at the end is just binary. You can also program in assembly, but that's just going to take like a really long time. I mean, yes, you can optimize a lot of things, but you will also be spending much more time on that. And then once we have this machine code, which is the binary, every position of the bit means something specific. So depending on the instruction that you're doing and how your bits are organized, like for example in here the machine code, it means like a specific thing on each of them. So here's how a typical instruction looks like. I'm not going to be explaining like everything in here, but just keep in mind that how you write your instruction and how it lays down on each of these specific field is how you're going to be having like your code being interpreted. Okay. And then this is how basically instructions are being executed inside your CPU. So the first step is the fetching. So the CPU reads the instruction at the address in the program counter. So basically the instruction, it's these. So it can be like add the register, add R1 plus R2 and store in register 0. So this code in assembly, it says that I'm going to add whatever is on register 1 plus whatever is on register 2, and then I'm going to store that in register 0. And that assembly code can basically be translated to this machine code, which is a binary in here. And then this binary code is the one that I'm processing here. So when I'm talking about instruction, by instruction, I mean what's in here, a 32-bit binary code. Then after reading the instruction and at the address in the program counter, then we're going to be doing the decoding. So for the decoding, the CPU looks at the bits to figure out the operation and operands. So if we're going to be adding, if we're going to be subtracting, or whatever operation we're going to be doing. And then after that, we're going to be executing. So the CPU performs the operation, so whatever operation we want to do. And finally, it's going to write the results stored in the destination register or whatever memory where we're going to be storing our instruction. Well, the result of our instruction. So this is the execution cycle that every instruction follows in your code. This is now going a bit more into the embedded systems section, but it's also important if you just want to understand these as well. Okay. And then going back now into the memory mapping section. So as I mentioned, it's very important that you are able to be familiar into reading the data sheet of your hardware. So when you get a new piece of hardware and you want to code it, you always want to check your data sheet. So in here, I place an example of the STM32 GPIO-A datasheet snippet. Why is it important to know the memory mapping now, relating everything that we saw on the bitwise operations and going back to these questions on what's the essence of shifting? So it's very important because in here you will have specific registers in specific memory addresses, and you want to make sure that you are shifting the correct bits in order to get the operation that you want. So hardware peripherals such as input and output ports, timers, communication protocols, they are all accessed as if they were memory locations. So a specific hexadecimal location. They live as at a specific fixed address in the memory map. So maybe I can have my GPIO 13 in address hexadecimal 3D or something, for example. And data sheets help us to specify these addresses using a base address for the peripheral and an offset for each register within it. In here we have an example. So in here we have the register name such as mode R, O type, ER, and so on. And then we have our base address, and then we have the offset. So let's say that I want to access the first register, which is mode ER. So I'm going to go and type the space address, and then I can just use the offset. So 0x00, but I need to keep the space address for everything. And then in here, you can basically see a description of each of these registers. So for example, the O type ER, which is the second one, it says that that one is a port output type register. And now seeing these, you already know these hexadecimal directions, they can also be typed into binary, but we use hexadecimal, so it's brief. You now understand what's a register, and you know that a register, it holds bits, so you know that you can store stuff in there. And from the memory map, what you need to know is that we will always have a base address for things, and then we are going to be having offsets for each different register, so we make sure that we access each register that we want. All right, so we're gonna go now into seeing an example in C for bare metal. And for these, we're not gonna be doing the walkway simulation. What we're gonna be doing is that I'm gonna be sharing this article that I found that I think that explains it explains bare metal with Arduino at a really nice level. So I'm just gonna go ahead and remove these. I'm gonna share my screen. Let me just change screens in here. So go ahead and enter that link that we're gonna be seeing this article in there. I'm also gonna be sharing that on screen in here. So basically, this is an article that I found on Arduino Uno comparison with bare metal in programming. Let me remove this one so you can also see it a bit better. Okay, so this is a really interesting question. So how do you program an Arduino Uno microcontroller bare metal? Where do you start with manipulating the processor memory directly? And then this is the example, right? So in Arduino, let me make this a bit bigger. If you want to turn on a LED, you set up your pin, and then you just do digital write, you set high, and then if you want to turn it off, you set it to low. So this is really simple, right? So turn the LED on, high is the voltage level, wait for a second with this delay, turn the LED off, and then wait for a second. So this is your regular C++ code. It's really simple. I mean, we are using these built-in functions to do whatever we want, but we cannot really control everything. So we are facing this question: how difficult can it be to write the same functionality in C without any abstractions or helpers? So now what we're going to be doing here is converting all this code into bare metal C. So the raw C that goes directly into what your hardware is reading. So in here, if you want to dive a bit into understanding how does a microcontroller memory work, which is basically what we've been explaining, you can go ahead and read this as well. It also refresh C pointers and accessing the registers. This is basically what I was explaining. Let's assume that bit 2 of a register should be set. The other bits of the register should not be changed. This can be achieved by using bitwise or operation to the register with a bit mask. And this is just the one of the examples that we were sharing. This one is for setting a bit of a register. So for example, if you want to set a number 1 in this register position, or if you want to delete a register, like for example, delete this position, which means set to 0, this is the code. Or you can make it like just like this. So this one is to set register. This one is to delete register. And then this is the memory addresses that I've been talking about. So this specifically comes in a data sheet. So this is something that you can find in the data sheet. So in here we have all of the pins, right? So we have a pin analog 0, analog 1, and so on. And we know that this pin is PC0. Then we also have the digital pins in here are like, for example, PB5, PB4, and so on. And we can see like all of the different pinout configurations for everything that's in here. Okay, and then for the data sheet, the first thing that you want to do is configure this specific register. So in a data sheet, you will find a lot of tables that look like this one that says DDRB, the port B data direction register, because it allows you to play around with the registers that you're going to be using in here. So in here, we know we have 8 bits named from 0, 1, 2, 3, whatever, into the 7-bit. Then we also have a base address in here, which is 0x04, and we have read-write values, and then we have the initial value. In this case, everything in my port B direction register is set to 0. So the port B data direction register, that's this. So if in here port B is from D13 to D8. So 1, 2, 3, 4, 5, 6, 7, 8. I have another PB5 in here. So PB5, and where's the other one? Because we have 1, 2, 3, 4, 5, 6, 7. I don't find the other PB. But yeah, this register is basically for all the port Bs. So all of the Bs that we find in here. And now let's say that I want to modify only the LED built in. So that's PB5, right? So in order to set the port B number 5, which is this one, we need to do bitwise operations in here. Why? Because if I turn on this one, it's going to be like the incorrect one in here. So it's not going to be the pin that I want to set. So the first thing that you want to do is configure the DDRB register and set the bit number 5 so we can use it as an output pin. So this one, the DDB5, because that one equals the LED built-in register in here. So to activate the pin and turn the light on, we need to set the register for number 5. So to do that, we do a bitwise operation. So we can set only the port B5, and then we onset the bit we use to mask it again as the following. So we need to do these 2 bitwise operations. That's why I was mentioning that is also important. And then this is basically the program. So you are setting your port a B5 as an output. Why? Because it's a LED, so it's going to be an output. Then you need to set a port B. We do a delay, and then we need to unset it because we want to do the low, so like turn the LED off and then do the delay again. So this delay, this is also another function that we need to code, and that function, it has to be down there somewhere. Not sure where it is. Oh, I think they're using they're using a library in here. We use the delay helper function to clock counting delays easier. But you can also do your own delay functions as well. We have a question here. If I want to buy a machine key to explore stuff about robotics, what do I buy? Is there a specific hardware name that's a bare metal that I can order? Also, could you advise I get an Arduino Uno, Raspberry Pi, or a bare metal? So everything can be programmed in bare metal. So as I was showing on this example, we have a basic Arduino in here. It's an Arduino Uno, and then you can either code these in basic Arduino code, or you can code it in C bare metal, like it is in here. So if you're just getting started in robotics, I will strongly recommend for you to buy an Arduino first and start playing around with these initial instructions. Try to check my stream on getting started with Arduino, watch a couple YouTube tutorials, and once you understand how all of these basic function works, then you can move on into coding in bare metal and moving on to more complex projects. But yeah, definitely get an Arduino first. They're also like much cheaper. I'm not sure if that's the R3. I think it's just a regular Arduino Uno. Yeah, it's your regular Arduino Uno. All right, awesome. So let me just go back in here and go back again. Okay, thanks. How about comparing a Raspberry Pi? So a Raspberry Pi, it's different. A Raspberry Pi, it's basically a mini computer. The difference between these two things is that an Arduino can only run like a specific thing. So it can only run like a script of code at the same time. And the Raspberry Pi is a computer, so you can basically have an operating system inside there. So you can have a Linux installed in there, and you can use it for much more harder projects. So, for example, if you are if you're going to be doing like, I don't know, a really complex IoT project, or if you're going to be training like a machine learning model or a computer vision model, then it will be nice to have a Raspberry Pi. Also, if you want to get more familiar with Linux and understand the terminal and all of that, you will go with a Raspberry Pi. But if you just want to understand like the hardware and controlling like peripherals, such as like motors, cameras, well, not cameras, like motors, LEDs, sensors, and so on, you want to go for the Arduino. What about an ESP32? Because I only have one. Yes, you can also use it to code in bare metal. So if you just do like a simple search, so for example, if I were to search ESP32, so you can look, for example, in here, like, okay, so getting started with bare metal ESP32 programming. And then you can see like the setup. So there's a lot of content that you can find in there. This one's better. I really like Medium articles. They're really nice. Yeah, so this is another example, bare metal ESP32 programmer, direct register access for LED control. So in here, they're basically showing the raw power of register level access. So like manipulating your registers with your base addresses, and then using the unsigned 32 integer amount. Yeah, I can send you this one if you want to see it. To be honest, it looks like really nice. So you can also learn from there, or you can also just search these online, like ESP32 bare metal code, and you will find a lot of tutorials as well, like blinking an LED with bare metal programming. And that's a YouTube video that uses ESP32. Great. So let me stop sharing this thing. All right, so thank you everyone for joining. As I mentioned, this was going to be a brief stream. I hope that you like learning about embedded systems. Again, this is just the tip of the iceberg. There's many things out there that you can research. I already gave you a couple of topics where you can get started. You can always reach out to me directly if you have any questions about anything, or you want to build a new project, or you're seeking advice for whatever projects you're doing. Feel free to reach out on my Discord DMs. You can always watch the stream recording on YouTube. And if you really like the stream, you can leave some feedback on this link. So mlh.link, global hack week feedback. So that's in here. So if you want to see something new on the streams, you want to add some feedback, something that you like, something that you didn't like, or just give a general shout out, feel free to leave it in there. All right, so thank you everyone. This was my last stream for Beginners Week. I will be back on the next Global Hack Week for sure, and I'm pretty confident that I'm gonna be bringing back more hardware streams because I'm pretty sure you are liking those. So yes, thank you everyone, and we'll see you soon. Bye.